Thanks for coming, guys. By the way, it's good to be back in person. Last time I did it online. So today I'm going to talk about time management in reinforcement learning. I'll try to make a case of why it's important to look at impact of the time resolution. Okay. So here's the outline. So first, I will motivate why we want to do time management in RL. And then I'll go through the problem setting of how we can characterize the impact of that. And that will be followed by some theoretical result and also simulation on both linear quadratic regulator and Majoko. All right, so let's start from this classic picture of agent environment interaction. So quoting the book, the agent and the environment interact at each of a sequence of discrete time steps, and t equals to 0, 1, 2, 3. And we end up getting trajectories like this, again, indexed by t, and t plus 1, t plus 2. Okay. And here the t refers to the time steps. And we might wonder, how does this step size translate into physical time, especially when we try to apply RL to physical systems that runs in continuous time. Okay, here are a few examples. We have the pendulum, mini cheetah in the real world. I also added some simulation there. All these systems run in continuous time, and they're controlled by algorithm that runs in discrete time. And there's a star there. That means, so in the simulation, there's no real continuous time, but they're run, so the simulators are run at a fairly high frequency as a proxy to the real continuous time system. Okay. And so where does the physical step size come in? It's hidden in the environment implementation. And I'll take OpenAI Gym, for example. If you look into the code, there's often this delta t, and that's defined by the model time step, which is just some quantity that's in the definition of the robot, and that combines with frame skip, so to give you some number, and that number never gets changed. So as a community, we optimize our algorithm for those fixed number. So the high-level picture looks like this. We have some system that runs in continuous time, and then we discretize it on some fixed step size. And the underlying system now becomes a discrete time system. And then we run RL, we run optimal control to maximize the return. But that return is for that discretized system. And I guess it kind of makes sense that the optimal step size would have some impact on the performance you're getting. And the question we're asking here is there an optimal step size? And if there is, whether the step size that we've been using is optimal. The return, yeah, because we're maximizing the return on these proxy systems. But what we really care about is the original systems. And that happens when we run, for example, sim to rail, and the real system runs in continuous time. So just wanted to look at the previous work. And we already know that temporal resolution is important. For example, we have the options framework, which is quite flexible and is used in many settings. And a specific instance of that is, oh, sorry, I have to explain what options is about. So it's about temporal abstraction. So you first commit to some temporal resolution, and then you decide whether you want to abstract that or you want to apply some control over a longer time span rather than just each single time steps. And it's quite flexible, and there are simple versions. One of them is called action repetition, where you simply would carry out the same action over some time sequence. And that's applied in both Atari and simulated control of robots. Oops. Okay. And so the underlying message of action repetition of that it helps in these simulated environments is that you probably want to go for higher temporal resolution, like a bigger step size than what is given by the environment. But there's also a different perspective. There are some works that find that a smaller step size is better. So that's kind of contradicting what we had from action repetition, but they're all relative anyway. So we can understand that as different scheme of things, and it could be dependent on the application. And so the important thing here is that we don't really understand the impact of temporal resolution in RL. We see empirical evidence, right? And some value is better than the others, but theoretically, we don't know what the landscape is. And so we want to analyze it. And how do we do it? So we start from some assumptions. First, we assume that samples arrive at discrete time points on a uniform clock cycle. That means we assume that the step size remains constant throughout. And we also assume that the horizon is uniform. That means every episode runs for the same length. And in the end, we also want to assume the data budget is finite, right? And which we think aligns with most of the settings in the real world. Okay, so here's what we want to get on a high level. Given finite data budget, and then if we pick some system that have analytic form of the dynamics and rewards, that makes it easier to analyze the system as opposed to some black box system. And then given those, if we add the objective of interaction with the system, for example, if we want to estimate value, we want that value to be accurate. So there are metrics that we can use. And so given those, we can arrive at potentially some trade-off that suggest there is an optimal value for the step size. Right. So the simple framework that we pick goes like this. First, we have a linear dynamical system. Right? And so this might not look familiar to people working on discrete time systems, but it is sort of the standard way of writing some dynamical system in continuous time. And here the WT is Wiener process. It's also called Brownian motion. And so this A tilde and B tilde are some matrices, and X are the state and U are the control. And the cost is assumed to be quadratic. It's also the simplest setting you can get. And the Q tilde and R tilde here are positive definite, so that guarantees you a positive cost. And then you would take the integral to get the cost for the entire trajectory. This is as opposed to taking the summation over discrete time steps. And then we also assume the simplest controller, which is just a static feedback of the state, right? And this controller K here is time invariant.
What is static feedback?
Static. So the question, I just repeat the question for the online audience, is what does static feedback mean? Okay. There are two parts, static and feedback. It just means that the control is feedback from the state that you observe, and static means it does not change, so that K is not changing over time.
Also, you don't learn this thing.
No, not in our set. Yeah. So assume it's fixed throughout. And then we can plug in this controller to simplify the system. Because it's a linear scheme on the dynamics, so everything becomes easy. So we end up getting this new differential equation that has this A. So that A is called closed loop control, closed loop dynamics. So it's the effect from both the original dynamics and the control that you apply. And so the cost can be simplified as well. And then we have this V term here that's familiar to our audience, is the expected cost. So here we're always thinking about cost rather than reward, but it's the same thing. Okay, so for the rest of the talk, sorry for the typo, we're gonna just be focusing on this simplified system. Okay. And there are this quantity here, tau, which is the system horizon. So that controls the, well, that's the cost that you want to estimate. We're going to introduce another horizon T later on. But for now, that's all you need to know. And there's an important assumption that the process starts from 0. Okay. We could make it more complicated by starting from some other constant. That is fine. It's just going to make the analysis more complicated. And for the ease of computation, that's what we choose. And there's another choice of making it random, of following some normal distribution. That's also possible, but again, it's even more complex. Okay, so just taking a look at the value function estimation. It's the integral of some cost that's instantaneous, and the expectation is with respect to some noise, and that noise was introduced by that winner process that I talked about. So the trajectory is going to look like this. Okay, so you run always from x0 equals to 0, and you each time you take a rollout of the same policy, it's going to give you different trajectories because of the noise. And that's what the expectation is with respect to. Okay, and so I wanted to, before I dive into the analysis, I want to just to give a 101 on winner process. This is just a screenshot from Wikipedia. So it has some important properties that makes our analysis way easier. The first, it starts from 0 almost shortly, and then it has independent increments. And so it's a nice feature for RL people, especially because it's Markov. And further, the increment that it has follows a Gaussian distribution. And also it's on a strictly continuous path, on every rollout you take. And now the reasons these properties are important is that it allows us to compute the stochastic integral, right? So, okay, I want to go back to this integral a bit. So for example, this integral here, this x includes this stochastic process, and we cannot take integral in the classical way. So we have to resort to some different machinery to deal with it. And so back to the framework, we need to ask. So that was the system setting. Now we want to estimate it, right? And we also want the simplest setting possible, right? And it is the Riemann estimate, right? So you just take discrete samples and then estimate the integral, based on the Riemann sum. It's pretty standard, and the value becomes an average of many trajectories, right? And this m denotes the number of trajectories. And remember that we have the fixed data budget denoted by B that equals to n times m. So here, the n is the number of data points on each trajectory. And the m here, as I said, is the number of trajectories you have. And so this estimation horizon T is where your data can cover. So given finite system horizon, they're the same thing. But if you think of a system that runs in infinite horizon, right? So we still want the value of the infinite horizon, but our data is only enough to cover just a part of it. So that's why it's important to distinguish them by having another quantity that denotes the horizon that your data can cover. That is the T here. And then we have this relation between n and T and H, where H is the step size. Questions? Or?
Where is tau? What is the relation between tau and n?
Oh, tau was the integrals from 0 to tau. So it's not here because in our estimator, we just are concerned with where the data can cover. So it can only cover up to T. So if the tau is the infinite horizon, yes. But in LQR, the linear quadratic regulator, for example, people are often concerned with the infinite horizon value estimation, in that you would run the system forever.
N would be infinite as well.
And will be finite. It's controlled by the data budget. So given a finite data budget, you can only have finite n.
May I ask a question?
All right, so. Okay,
Hello, may I ask a question?
We will want to go from here is that we want to quantify the error in our value estimator and then decompose it to different two different parts.
Vincent,
the approximation error and the statistical error. Yeah, and we'll
Vincent,
go through
there's
the
a question
details
being
of it.
posed. Vincent, there's a question being posed.
Now the problem setting, just to summarize, we run Monte Carlo, based on a Riemann estimator, and to estimate the value, and that's given a finite sample budget B and a stable policy. Right? And the stable policy is just so that the cost doesn't get crazy, because here the system state is unconstrained. It could go to infinity, and you can get, if it is unstable, then you can get infinite cost, and we're not really interested in that setting. And the objective here is to pick the temporal step size H such that some metric is minimized, and that metric would choose the mean squared error. And so the quantity V hat here is the Monte Carlo value estimate that I went through. So you would take many trajectories with discrete time sample, and you would take the average of them. And there's this V here that denotes the ground truth value. That is the true expected cost. And you want to minimize the error. And so to start the analysis, we first look into the scalar case, where there's no longer any matrices, it's just a scalar. And that reduces to this Ornstein-Uhlenbeck process, which is also kind of common in Temporal setting, but it's used to model the noise rather than the system. And here, because we assume a stable controller, this A is smaller than 0, and that would make it mean reverting, so that is stable. The objective is, again, the same thing. And I just wanted to make the parameters more clear here. We have the step size H that we want to optimize. We're given this data budget B. And this estimation horizon T is something we can choose. And the rest are system parameters. This Q here, we're gonna omit it in the rest of the analysis because it can factor out from this metric. And we just set it to 1 without loss of generality. And this Q was from the cost parameter in the vector case. Right. So any questions so far on the setting before I dive into the analysis? Oh, okay.
There's a question online.
Yeah, sorry, I didn't see it. So I'll just read the questions based on the order. Is the episode length in terms of the continuous time? Same question for finite budget case. Yes, so it's wall clock time. Yeah, thank you for the question. And the second question is, do you know closed form expressions of the values in this case? Yes, that's what having all those simplest setting of the system gives us. What?
You set your speaker to on.
To
People online ask questions, we cannot hear them.
oh, I don't know how to option. Oh, there's
No.
Oh, because I minimized it.
Where is your
Oh, there.
yeah, here.
Okay.
Speaker, choose
This one. Yeah, sorry. Is that good now?
if people online can speak test.
Oh, so that I can hear them?
Yeah, if they
Can
ask.
someone online say something? Or if you have questions, just ask the question. Or just testing the audio. Oh, I didn't hear anything, but I.
You hear me, Vincent?
Oh, yes. Yeah. Thanks,
Can you hear
Roshan.
me?
Yes. Thanks. It works. Oh, good. Now back to the presentation. All right. All right. Okay. So now we are gonna characterize the MSE of the scalar system. And we had that metric. And then when we write down, like we basically write out everything because we have the analytic form for them. What we end up getting is this long expression. It's hard to parse, but the idea here is that at least we have something some exact expression of the MSE. So we can exactly quantify the error. And that's important when we started this work, that we want to start from exact result rather than bounds. Because if we start from bounds, then it's harder to quantify the optimal step size. And so how do we get to this expression? Okay. So let's go through the proof. Okay, it's very easy. That's it. Oh, I just included this slide from Francesco, so because I find it funny. All right, so well, you can at least tell that it takes some space to write it out. Why is that? As I said earlier, now the integral contains something random, and then we need some different machinery to handle that. We have, this is a closed form expression for xt. And the machinery we used is called stochastic calculus. There are different terms here, for people who are not familiar, you can look it up. So by using these machineries, where we got was these expressions. These higher order moments, like second order, fourth moments, and these cross terms. And those are just a result from expanding the MSE. Okay, so recall that this left-hand side is the original objective. Then we can expand it, simple to here. But when we plug in the formula for xt, we get these squares and squares, right? And there's also double sum inside. So when you fully expand them, you end up getting a lot of terms that contains these higher order moments. But given those, a closed form expression, we can just plug them in and try to compute the final result, which is quite cumbersome. That's why it took a lot of space. But now the problem is the result is so long that it's hard to parse. Right? So one way is to further simplify this setting by just setting a to 0. And then we just have a scaled Wiener process. And that turns out to highly simplify the MSE. Now we can look at the order of H, which is what we care about. So there are first this H square term. If I make H smaller, so taking smaller step size, it's going to reduce eventually to 0. And that's the approximation error from the Riemann estimation, the Riemann sum estimator. And we also have this term controlled by both H and B. So in fact, I didn't put the expression here. You can write it as 1. So there's a T on the denominator. So we can combine them, which gives 1 over m. The m is the number of trajectories. And that means as the number of trajectories goes up, this error reduces. And that's the variance term here. So it makes sense that we want more trajectories to reduce the variance because there's noise. And the rest of the terms are just some higher order terms that becomes small in the asymptotic case, and we don't really want to worry about them because B is often fairly large and H is small. So, and from there, what it gives us is the H star. Right? We can just make the set the derivative of this expression to 0 and get the H star. And there we can check, okay, the optimal step size depends on the data budget in the following way. Right? And it's nice, and we'll but we'll talk about the more implications at the experiments section.
Say the rightmost term is can be ignored because you have h is usually small, right? Instead, right? So the first term that you said has to be just together. Even one constant. So that's h squared, right? And then you have an h term for small step size, for the h term that's large. But
can you figure out what B is? Because you have the relationship B has, I mean, the H and B are related, right? So it seems to me, it's not trivial to me that the rightmost term is small the way it's written there.
Good question. I would repeat the question for the online audience. Martin was asking, how can we ignore these terms in the black circle, right? We're not in the asymptotic case, right? B could be small and H could be big to some extent. And you're right.
H is small, right? H is supposed to be small.
H is small, but it's not like really zero, right? So in some sense, it's.
So that means that the H squared is way smaller than H, right? And therefore, any term that has H not squared would be suspicious to be larger than H squared.
Right. So, so the answer are there are several aspects to this. So first, here we're in the setting where we want to understand the order. So to parse the result. So we do have the exact result earlier. So that's gives the full, the accurate MSE. But here we can check the order in a different way that we'll show on the next slide. So here I'm just going through the simple setting and try to parse the result. But if we're concerned with this truncation errors.
Actually, the way you want to show it is you want to take your formula for B, and B is T over H. So now that T over H multiplies the H on top, and you have an H squared on top, and that way you show that the two terms are of the same order, right?
Okay.
So it's actually H squared in the rightmost term if you just plug in the B equals T over H. Yeah,
so Martin was saying that you can rewrite B as some function on H and to to further analyze the order of this. And but we actually want the finite data budget to be in the expression because we want to understand how it depends on the budget. And so
but you need the other form to show that the first and the second term have the same order. Like you need to have an H squared.
For the
rightmost term to show that that term has the same order as the first term.
Yeah. So because basically here, like we even look at the terms that without H, it's just fixed when you are given some fixed data budget. So we don't really care about it. And the rest are asymptotically, they're smaller. So we're not too concerned. But yes, in the non-asymptotic regime, we need to be cautious, and I will show some bounds that would help characterize that. Is that answering your question?
Okay.
Okay. So yeah, and we also can plug in the H star back to get the MSE, and that will help us understand the order of the error of your value estimation on B. Okay. And now we were in the A equal to 0 setting. Now back to the general setting, when A is not equal to 0, there are two ways to deal with it in order to get some expression that we can understand better. The first way is to take Taylor expansion. So this term on the top right is just to remind you of what the expression looked like originally. And you can just take Taylor expansion, and that will give you the order. And note that the order on H and B are the same as what we just saw in the simple case. And that, of course, is truncating some higher order terms.
Taylor expansion in H.
Yes.
Given D and H.
Yes. because T and A are fixed in this setting. It's given by the system, and we're in the finite horizon setting, so that T is P and tau are both equal and finite. Okay, so now how do we know that the higher order terms don't really matter that much? We now look at the bounds. We can derive these lower and upper bound that both have the same order on H and B again. And yet again, they are the same. So the order are the same as the result from theta expansion. So they're quite consistent. And so Martin, that's what I was referring to when we talked about the truncation terms or in the last slide. Hope that further address your question. Anyway, and the same thing happens here where we can derive the optimal step size H star. Okay? And that has the same dependence on B as we saw early on in the simple case. So, oh, sorry. There, okay. So the same dependence on B, 1 over B to 1/3 here. 1 over B to 1/3. Okay. All right, so I think that's it for finite horizon, and it's on this content. And I think it's important that we note the big picture that there are still many other cases where we need to take care of vector and vector case, and also add discounting factor. And also further, we have the infinite horizon set. Okay. So let's address these discounted and vector setting. And so add discounting factor to the original result of the undiscounted case is almost trivial. So you end up getting this expression. And extending to vector case is a bit more cumbersome, but it's again doable, and you end up getting some order on H and B that looks the same, right? And the constant, of course, it now is more complicated. It depends on the eigenvalue of the system parameters. Now we have a matrices, and the assumption here is that the system matrix A is diagonalizable, just to make it easier to analyze. But if we go from diagonalizable to general matrix, that's not necessarily diagonalizable. We can still analyze it, but we have to forego the exact MSE. But instead, we can have tight bounds. And so the order would be the same as you're saying here. And just to justify the assumption, we essentially assume that the system is controllable. That's the controllability is a term in optimal control that essentially allows you to freely adjust your eigenvalue of the matrix A. And then you can then choose them to be generating a diagonalizable A. Okay, so now we move on to the infinite horizon setting. Now the difference is that the trade-off. So again, we have this approximation and this statistical error term. And that's the variance, right?
I was curious. So for the finite horizon, you set up your system where you have the bounded amount of computation B.
Mm-hmm.
Would the expression in any way be less? I mean, couldn't you, without less of generality, simply set B to a fixed value? Or because what you're looking at as the overall order H, right? Mm-hmm. The order of H.
Yeah, because I guess the question from Martin is that can't you just set B to a constant to make it easier, right? But we also want to get the H, the optimal H step size. as a function of the data budget B. Because we want to show that as you vary your data budget and potentially to infinite, how the landscape of the H star look like.
Okay.
Yeah. Now we move on to the infinite horizon setting. Now we still have finite data, so estimation horizon T is finite. But it's not enough to cover the full system horizon tau, which is now infinite. So we now suffer an additional truncation error on that part that we cannot cover with data. But apart from that, the result looks very similar. Now if you notice, the order of H changes. Right? But there's still this approximation error and these statistical error term. So those are still the same. And we can still write H star. Now it depends on B with a different order, 1/5 instead of 1/3 before. And so that's the scalar case, and we can extend it to the vector case here. And if you compare the order of H, they are the same. That's the same as the results in the finite horizon case. So making it vector doesn't really change the order that much. There's something about the assumption that's not quite important. Let's skip this. Okay, still have some time. Numerical study. We did experiments on both synthetic instance of LQR, and we also did some experiments on nonlinear systems. 8 environments listed here. And so now I want to, before I show the results, I want to talk about the policy side of things. So we have to start with a stable policy. And the way we train it is just by some algorithm that's not sensitive to the time step. And then it's not optimal in any sense, but we essentially just look at the visualization and find a reasonable policy that can flip the pendulum and make it stay upright, and also make the robot run in an okay-ish manner. Right, so that's the and another thing is, note that the assumptions we make, at least some of them in the LQR setting, is no longer true in the nonlinear system. First, they're nonlinear, of course, and also they don't start from 0. They start from a random state that follows some normal distribution usually, and but the transition is fully deterministic. But that combined with the random starting state still makes it random, but it's just random in a different way than what we did in our analysis. Okay, so first, some result on LQR. Now you're seeing the MSE, so where we assume that there is some sweet spot on H. So on the H axis, we have the step size H, and on the vertical, we have MSE. So we hypothesize that there's a trade-off, there's a sweet spot on the H star, and we observe that indeed in LQR. And the different plots are just for some different systems. On the left, too, we have scalar system, finite horizon. On the third plot, we have a vector system with finite horizon, and then we move on to the infinite horizon setting. You can see that because of the truncation error, that the data isn't covering the full trajectory, the error now becomes a lot larger than the other plots, but the trade-off remains.
What is N?
And it's the number of dimensions of the system.
And when you say vary K, what does that mean?
Okay. Yeah, sorry. So the A is now the scalar, so that determines the transition. Yeah, I'm just varying the data budget and the systems to see if the trade-off still holds.
And A1, A2, what is it?
Sorry?
A1, A2.
Oh, A1, yeah, sorry, I should explain that. Good question. So the question was, what is A1 all the way to A5? That's just some random matrices that we generated. And also 2 plots on the right have different A1 to A5. So they're just fully random.
How well do these fit with the equation? So we had nice equations for MSE in terms of
Yes.
edge and edge.
Yes.
Edge dependent.
Yeah. So how well does it align with the analysis? It's on the next slide.
Oh.
So the solid line is again what we observe in practice, and the dotted line are from our analysis. So we plot the exact MSE on these plots just to see if they align. We'll also plot the approximate MSE. So that's the MSE we got from applying Taylor expansion and ignore some higher order terms. You can observe that is on the left end, things are very well aligned, but on the right, as H gets bigger, you start to see some gap between the analysis and the empirical. But in practice, we very often than not, the H is quite small anyway. So it's all right to have those error. And now we move on to nonlinear experiments. And it's the same type of plot where you see the vertical as the MSE and H, the step size on the horizontal. And the different lines represent the result from a different sample budget. So we increase the budget just to see how the optimal H shifts. And we're going to get to that on the next slide, but note that the MSE is there. It's quite visible, and some details on how we did it. It's a policy that's trained by some algorithm that works well for different time steps. And we have to have a proxy to continuous time system. Because we talk about the true value being the value for continuous time system, which we don't have. Right? But what we can is to modify the original Majorco systems to run at a delta t that's super small, and as a proxy to the continuous time. And the true value, we don't have it, but it can be approximated by averaging the return of just a huge number of episodes. And we verify that if you go even further to like even double or triple the episodes, the value stays quite consistent. So we stop at 150K.
B naught. What is the value of B naught?
B naught. B naught. Oh, yes. Sorry. The question is, what is B naught on the plot? It's just like a base data budget that's enough to cover at least one full trajectory. So like, for example, in when you choose very small H, even one trajectory accounts for many samples. And the B naught better be larger than that. And so that's how we pick the B naught. So just at least giving you one trajectory for all the H considered in the plots. And then we want to understand the H star dependence on B naught, on B. And so that's why we make it larger. And from there, we can extract a second plot, which is the dependence of H star that we observe as a function of the data budget B. Now, this is to understand whether that relations we found in analysis would indeed, how well it aligns with the nonlinear setting. So what we did is that we assume that it's the same dependence, but just vary the constant. And then we can fit a line. So assume that that B to the 1/3 dependence and then we fit a line based on the data. And you can see that it aligns very well across the experiments. Okay, by the way, the dashed line is the fitted line. The solid line are the what we observe from the experiments. Okay, so it's coming to the end of it. The last thing is in the title, I talked about managing the time horizon, the temporal resolution, but we haven't talked about yet. And so the short answer is that we don't have a perfect way yet, but we can at least give some guidelines. So first, we have those H star, those dependence from the analysis. And what we can do is that we can, like on a reduced data budget, we can evaluate the performance of different step size. We still compute the MSE, and then we find where the H star is, and we can do the same plot and try to fit the line by least squares. And that will give us the constant, and then which can be used to extrapolate to larger B. Now, the catch here is that we no longer have a great accuracy on B, right? That's a true value. So we can only work with the amount of data that we have. But I think it's still possible because we do still have a lot of, so the estimator itself don't really have as much data because of the data budget, but then the outer expectation. So when we run these experiments, we do run multiple trials, like 50 trials. And you can use all those trials. Well, you can't use that on your estimator itself, but you can use all of them for computing your B. So that will give you a bit more data to work with. And then that's the scheme where you can try to use in practice. No, we're not saying it's perfect, but at least it gives a starting point. Okay, so to conclude, so we did a precise characterization of the different errors in the Monte Carlo value estimation in LQR. And it suggests that there's a fundamental trade-off that's modulated by temporal discretization H, this step size. And the trade-off even aligns well with nonlinear systems. And for future work, so this is just a starting point. It's simple Monte Carlo, and we're not doing control, it's just value estimation. So there's a lot of future work, including, we probably want to use a better algorithm, temporal differencing or system identification, or model-based in RL terminology. And we want to also optimize the policy. And there that have further challenges, including what if you want to discretize your policy at a different step size, and then you have two different time scales, it's even harder to handle. And we can also try to analyze nonlinear systems by taking local linearization. And yeah, that's it. Thank you for your attention.